Alrighty, my name's Liam. I'm giving this talk. Hello. I'm from Australia, Brisbane, to be exact. So, pardon any flubs. I promise it's jet lag. So, like I said before, I'm Liam. I'm a lead cloud engineer in modern deployments. I've been at Octopus for about 4 years, but I've worked with Kubernetes for about 9, since about 1.5. Originally, I was a systems engineer, pulling things in and out of racks, dealing with networks, all of that fun stuff. Then I decided that SLAs and SLOs were my deal, and I became an SRE. Then I became a cloud engineer because that's what people wanted me to do. At the moment, I'm really writing software in Go and C#, and I'm trying to mix in a lot of my reliability experience with that to try and get the best possible software outcomes as we possibly can at Octopus Deploy. So, what we built. In Octopus Deploy, the modern deployments team is kind of like the Kubernetes team. And inside that modern deployments Kubernetes team, I'm the Kubernetes guy. And so this talk is really about my personal experience trying to build a piece of software that we call the Kubernetes monitor. It's a component of Octopus Deploy. It runs in customer clusters. And when people deploy with Octopus Deploy to those clusters, essentially what happens is the monitor goes through, has a look at what's there, and sends back resources and the current status of things. It sends that over gRPC. It's really cool. It was very fun to build. And customers just install it by Helm. The catch is, yeah, we ship that software using Helm. For me, as an SRE, that makes things like right-sizing, performance engineering, debugging, and no SLOs or SLAs. It's terrible. Can't do any of it. So, before we get too far in, a quick show of hands here. How many of you guys, at some point, have just picked a random resource, limit, anything like that? Oh, yeah. Come on, don't lie. We're not going to judge you here. Yeah. No. Now, we almost fell into a very similar trap, but just by setting performance targets. Again, we can't see anything in these clusters. So we need to have like a baseline, a default to give to people. But we didn't have that at the time. We kind of threw some numbers at the wall. We kind of tried to talk to people and figure out what that number should be. But they just didn't have any context. We were just like, I think at the end we just went, you know what, we want it to be fast and responsive. That's not a number, unfortunately. So I think we tried to approach this a little bit differently. We didn't start by hitting an arbitrary goal. What we wanted to do was to observe how this kind of thing ran in customer environments. We wanted to understand how these various things that a customer cluster might have can impact our software. Then we can use it to set targets. Unfortunately, customer environments are a little bit varied. We spoke to engineers using Kubernetes all over the world, both customers of Octopus Deploy, but also just people who would talk to me. Sorry if you got a random message on LinkedIn with me saying, hello, please, do you run 5,000 nodes in your cluster? Some people said yes, which was fun. But essentially, we just tried to shape our approach around all these different kind of use cases that people might have. These aren't hypotheticals either. These are all like actual workloads we wanted to support. I think actually Atlanta-based the tiny edge clusters on Raspberry Pi nodes, I think that's actually known at the moment as the Chick-fil-A model. Big ups to Chick-fil-A. That's great food, great Kubernetes. But yeah, the variety of these different kind of clusters means we can't just support a single pattern, right? Because some of them are gigantic nodes, gigantic clusters. Some of them are tiny clusters, but super underpowered nodes. So we started talking about the kind of load characteristics that these kinds of clusters might have. You know, we had like deterministic CI and CD. So, you know, every few hours, a whole bunch of stuff would come up, a whole bunch of stuff would get deleted. That's great. We spoke to people that were running game servers, you know, stateful pods that need to be up for, you know, honestly like the lifetime of me, not the lifetime of the cluster. And then things like multi-tenant platforms, where the platform engineers we were talking to had literally zero idea about what was actually running in their clusters, and they just went, the CPU spikes every like 3 weeks-ish, who knows? That made our life really hard, again. But we wanted to try and validate our software against this. So we did our best. We picked some metrics. First, CPU and memory, obviously. We want to be able to give customers the resource expectations. We don't want to be the guys at the back that just throw CPU and memory metrics at a wall. But we also wanted to deal with some UX metrics as well. So the latency, which is essentially how long it takes for something to change in Kubernetes, be detected, and then sent back to the Octopus server, we needed to know what that is. Customers can't set it, obviously, but if it's slow, customers will call us, and customers calling us is scary. So we created a load test cluster. We needed to test across a few dimensions. Specifically, we needed to test the scale, so how many things are inside of that cluster at the time. The load, which is the rate of change of events, what's going through in that cluster. And the length, which is just how long has it been running, because everybody here probably, I hope, has dealt with a memory leak before. I certainly have. The other thing we wanted to be careful about is the kind of scale targets that we're setting at. So when we were speaking to all of these customers, we kind of had a fairly decent idea about how many kind of resources are in a normal Kubernetes cluster. Turns out it's around 10,000-ish resources in like a fairly large size Kubernetes cluster. That's what we decided to kind of class as normal. Kubernetes actually has a scale target, which you can have a look at. I believe it's something around the lines of like 100,000 pods is kind of like where we set our scale limits at. So we kind of also wanted to just see what happened if that was the case. If we had, like Google or something as our customer, what would happen? So we tried to do a stress test as well to kind of just break something. That was fun. Turns out that's not free. If only I'd read Reddit before I tried to do this, I would have gotten a warning from some other guy who spent, $120,000 in 5 days doing performance testing. Don't do that, that's not fun. And yeah, it just ends up not being feasible for testing, because you do it once, you get yelled at, and then you don't do it again. So we found something better. We used Quok. This is Kubernetes without a kubelet. It's a SIG scheduling project. Hat tip to Shiming, who is the primary maintainer of it at the moment. Great work. It's a small binary, and it simulates the lifecycle of fake pods and nodes and other resources that are in the cluster. It means that for us, we can simulate load in our application and shove just a whole bunch of load into it and see how it reacts. This gave us a tool that we could use to quickly, reliably, and locally test out what we were doing. So we wrote some test suites. We did some load testing suites, which let us test against each of the workload patterns we were talking about before. And we did some stress testing, which is just a whole bunch of testing that we did where nodes would come up, down, pods would be created left, right, and center, deleted all over the place, lots of changes, just to see what happened. That was great fun, but even after doing all of that, turns out that things were still breaking in even just our test cluster, and we didn't really know why. And it's probably because things fail in Kubernetes in fun ways sometimes. Networks drop packets, the API server goes away, nodes die, a whole bunch of stuff happens. So we then used Chaos Mesh. We can run experiments to validate a whole bunch of stuff, including network chaos, pod chaos, stress chaos, whole bunch of fun stuff. It's a great project. Check it out. It's also CNCF. So after all of that testing, we found lots of performance issues. We realized that there's a lot of things that could go wrong. But now we had the ability to test it. we had the ability to make sure that all of these things that were happening, they definitely could be reproduced. And it was really the foundation for our effective observability, because it let us know where we needed to start focusing and let us understand the limits of our software and where to kind of let it go. And now we get into really the meat of this talk, which is the why, which is what observability is all about, really. We knew what parts were bad, but how on earth can we find the cause? And more importantly, how do we debug the performance issues when we're not sure where they're from? So we needed to instrument. We used, in our case, a mix of Pyroscope, eBPF, and OpenTelemetry, specifically traces. So first, Pyroscope. Unlike traditional profiling, if you guys have ever done profiling in a Go application, it constantly collects profiling information in a running application and just ships it to a server later to analyze it. You can go through, you can do diffs in between two different versions of your application running and kind of see what the memory, the allocations, everything is going on. We enabled this by default in all of our debug builds. Developers just ran the Pyroscope server locally, so they could look back on any of the problems that they found, if they found any. Now, dev time wasn't the only time we ran it. We also enabled it when we ran our tests in CI. We would run locally and ship locally to the local collector, but when we ran in CI, we shipped it to a shared Pyroscope server. And that let multiple people go in and diagnose any kind of performance problems running in any of our CI systems. So when we ran the tests, and we started to see spikes of CPU and memory, because we can't see this in production, that's where we would have to start having a look. And that kind of information was incredibly important. We could immediately jump in, have a look at the flame graph, find the issue, and fix it. The barrier to entry for any developers working on performance was way lower. In action, this is a quick example. This is actually the after photo of the flame graph. It's a little bit small, so you can see it's like 17 megs or something like that. But we found that all of our memory was growing constantly over time. Using the diff view, what we ended up seeing is that the deserializer was using up just a whole bunch of memory and just never letting it go. Turns out that we were accidentally retaining literally everything because of a pointer that never went out of scope because it was in a Go routine. I'm fairly certain that one was my fault. But on top of that, on top of Pyroscope, which is really cool, we also introduced another level of debugging, specifically for our test clusters, and we introduced Pixie. Now, Pixie is an eBPF tool that you can use to essentially go through and instrument anything that you might want to use. It lets you observe every system call, almost. It lets you do a whole bunch of network packet debugging, a whole bunch of function call debugging to kind of just see exactly what's going on in your cluster. It's installed as an operator, just runs on every single node. And it also profiles, which is really neat. Some of the other things we used were live debugging, which means you can just kind of log out exactly what's going on in the cluster, kind of without having to redeploy everything. And that helps when you're just trying to figure out what the heck is going on in your application. And the reason we used eBPF is because it's not always perfect to instrument with Pyroscope. I'm not a physicist, but there is a really cool quantum physics experiment called the double slit experiment. I won't go too deeply in it, and if anybody here is a physicist, please don't beat me up. But in the end, the result of the experiment is that light behaves differently if you observe it. Turns out your software is the exact same. When you observe things with Pyroscope, sometimes the pauses that it does, sometimes all of the collection that it does, slows down your application just enough that you don't hit that race condition you were chasing. So this meant that Pixie was really good at finding some very, very particular classes of issues, especially if telemetry was actually causing the problem. So now we had like really great tests. We had really good tools to debug. We gained a whole bunch of these granular insights, but at the same time, we kind of accidentally lost the big picture. So what we were actually trying to figure out was what do the customers experience, right? Like what do people see when they run this in their cluster? Not just the administrators hosting the software, but also the people looking at the UI. Now, what we actually wanted to know was how long did it take for a change to occur in Kubernetes, and then how does it show up in the front end of of our application? The why is why we have all of our debugging tools. To use traces well, really, you need to ship them somewhere. OpenTelemetry is just a format and a protocol. Locally, we set up Jaeger. It's just a Docker file, really easy to use, easy to set up, but it can be a little hard to connect the dots sometimes. Eventually, we ended up using Honeycomb for our remote traces. That's just because we already had it and we were already using it. But it was very good for shared environments, and it's really good for exploration. Pretty much any observability tool down in the showcase. I know Dash-O was here just earlier talking about that. Pretty much any of those will work with traces and will give you a really nice exploration view. A lot better than Jaeger's, at least. As a quick example of how we used this kind of observability stack to diagnose a performance problem locally, we were seeing a strange issue where all of our traces were fast. So everything was, like under 100 milliseconds. The CPU was like perfectly fine, not being hammered at all. The memory was high, but it wasn't crazy. But yeah, everything was still really slow. We had a look at the traces, and what we did see is that there were a whole bunch of empty spaces in between each trace. That pointed us down to Pyroscope, where we saw a big block of mutexes, specifically mutex contentions, which is when there's a whole bunch of things waiting on a mutex. I, again, had screwed up because we were queuing like we were in the UK, like it's a sport. Every time we had bursts of resource changes, each send takes around 50 milliseconds over gRPC. When you're doing 10,000 of those, though, that ends up being about 8 minutes of time you're waiting. So if you accidentally put a mutex contention right in the beginning of you trying to send to gRPC, it's not the network slowing you down. It's not, you trying to process the data. It's nothing like that. It's all you. So yeah, when you did that, all the operations got saved to memory, and that also then led to memory spikes, which we thought, oh my gosh, it's the memory. The memory is causing the issue. No, it was me. So we fixed it. Once we knew what was going on, it was probably the easiest fix that we did in the entire application. It was, just an accidental mutex call. We took it out. We used actual proper Go architecture and used channels and no locking, and it worked really well. We didn't want this to happen again. So how did we make sure that we didn't reintroduce a bug like this in future? So we just set up a whole bunch of automatic tests. We're a bunch of developers. We started running Quok clusters with baseline load profiles. We ran the monitor against them. We got all of the metrics, traces, and profiling data. We saved them to artifacts. And we just tested that the P95 reconcile time just didn't exceed our performance targets. We did the same with our memory and CPU usage as well, making sure that they didn't exceed the targets that we'd set before. And for the problems that we couldn't anticipate, we ran the latest version, the latest build of the monitor in a test cluster with a reasonable load. We didn't want to spend, $20,000 every 5 days trying to load test this. but we did have telemetry running against it, and we did have our chaos tests. This gave us a whole bunch of historical data that let us test out whether we'd been causing any regressions and kind of in what area that might be. And that was very useful. So should you do this too? Like, it was a lot of effort to get all of this done. We were forced down this path because we had limited access to clusters and a wide variety of load profiles. That may not match what you guys do. Unfortunately, the more that I think about this, the more I think that like even software that you build and host yourself should really have performance as a key feature, right? It shortens the feedback loop for your developers so that your performance stuff gets caught really early in the PR, not in the, in customers. Nobody here likes getting called out at 2 a.m. The other thing that this does is it gave us an opportunity to start making a framework for other developers in our company to start implementing something similar. So I started making a little just 5-step piece of paper that we could give to other teams to let them know what to do. So the first step was to understand your characteristics. We didn't want people to start with arbitrary targets and try to hit them. That was never going to work. They needed to talk to engineers that were going to use their software, whether that was internal or external, whether it was customers or not. We needed to get people to learn and run with actual real scenarios. The next is to instrument everything from day one. Developers love to just write logs and print them out, but it's just as easy to do that with traces. It's easy to do it with pretty much anything. Run Pyroscope, run Pixie in your cluster, any kind of other eBPF observability. It's really easy to just slot on in, and it's so low overhead that it's worth it every single time. And then make it easy for developers. Have a Docker file that runs locally so that you can actually see everything. Otherwise, people aren't going to use it, at least not locally. Step 3 is to observe the system under actually realistic load. So deploy to test environments really early, really often. Attempt to simulate actual real usage. And if you can't simulate real usage, use Quoc or some kind of autocannon, other HTTP traffic generators. K3s is a good one. And watch for load patterns that actually drive up your resource utilization. Like, that's going to be a very specific thing that you'll need to be looking for. When you identify bottlenecks, you should be doing it through profiling. Don't look at something and go, oh, I know where that is, I'm going to make a change. Try and make it so that you can see it, because that's going to help you find it in the future as well. Set your minimum performance thresholds. This is pretty self-explanatory. Just have a look at what you're doing and actually set some numbers. The key point here, though, is to document it and to validate it. Make sure that you're actually hitting it at the moment, because nobody likes a test that's going off every 5 seconds. And to document it, because otherwise nobody's going to know what you did. Last but not least, automate the process. Nobody does a manual process. It'll never happen. Use targets to validate the load, and then frequently stress the system to see where everything falls down. Do that without having to do it yourself. Do it automatically. So by the end of all of this work, what we actually had is a really cool little application that performed well in a wide variety of use cases. It recovers well, it's got really predictable resource requirements, and it recovers from failure. And we had engineers that don't get paged and also know when they need to stop optimizing and start writing features again. Thank you. That's been my slide deck and also my talk. I've got an examples repository coming soon so that people can actually start having a look at some of the actual YAML that we use to do chaos testing and a whole bunch of Quoc testing and all of our Pyroscope stuff. And if anybody has any questions, you're welcome to ask. Yes.
Hey, do you have any issues with deploying Pixie because of root permissions? Our pods are non-root, so does it not need root to run eBPF?
Oh, sorry, I can't hear you very well.
Oh, so, your Pixie, when you deployed Pixie for eBPF,
Yes.
did you need root privilege to do this? How does it run without root?
Yeah, so it does need privileged pods because it's a daemon set and it runs in kernel. It needs to install trace points into the kernel. So it runs as a daemon set, which is essentially the bit that kind of injects eBPF in there, and then a whole bunch of other supporting pods like NATs and a whole bunch of other things that allow you to extract that data from the cluster.
So you installed it on all nodes?
Yes, it gets installed on all nodes because
As a daemon set? Okay.
you can set it up so that it only gets installed on particular worker nodes, but it does lose a little bit of its functionality if you do that.
And does it only track eBPF on the host node, or does it actually go into the containers, into the pods?
No, it only runs all of the eBPF stuff because it's kernel. It'll only run it on the host node.
All right, thank you.
Awesome, thank you. Any other questions? The mic is right there. I promise I don't bite.
Hi. I don't know if I'm totally going down the down low level enough right now. I'm still trying to understand our interaction between our NLB and Kong data plane, and Quark seems like it could maybe help us out in that regard.
Sorry, again, I think the mics aren't pointing at me, so I can barely hear.
I'm still trying to understand our interaction between AWS NLB and our Kong data plane. And when Carpenter does certain things, it drops Kong on us. And we're trying to understand like what's the best way to test something like that. And would Quark give us that edge? Would Quark allow us to do something like that?
Yeah, Pixie is really good because it does allow you to see those kinds of drops. It lets you see like latency and stuff like that. If you want to test your software, Chaos Mesh allows you to replicate those kinds of things.
We're not even there yet. We're just still trying to get the interaction of like, can we get things into the cluster and like when it scales to not drop data, not drop RPS.
Yeah. So Pixie is generally very good for that because it's got kernel level access and it essentially runs in the user space, well, it runs in the kernel context. It essentially is able to see all of the traffic that is going through the kernel, which is going to be all of your routed traffic. So as you go through and you might get some connection drops or something like that, you can kind of see whether that's happening, like where exactly that's happening, whether it's happening at the container level, whether it's happening at the node level, and you'll usually be able to see, if like a specific system call that failed. Like sometimes you'll fail to like create a TCP session. Sometimes a TCP session is already created and it'll be, killed off because of a timeout or something along those lines.
And Quark I wouldn't really use in cluster. That would be something I would use like on Minikube locally.
It's a little bit harder on something like Minikube because Minikube, depending on how you run it, is running on your local machine, and you do need kernel level access. So if you're running Minikube on, say, a virtual machine, or if you're running on a Mac or a Windows machine, you're running in WSL. WSL, I'm not certain on. Minikube.
So we could use Quark to simulate nodes in a real cluster?
Yeah, so it gets installed onto the node in the cluster, but you do it via a daemon set, yeah.
Yeah, that's kind of mind-blowing for me right now.
There's a lot of really good resources about Pixie on their website and kind of goes into how it works. A lot of it is very low level into how containers work and how the kernel is shared.
What exactly is a node in Quark, like if I'm simulating a node?
A node in Quark?
Yeah.
A node in Quark is, well, actually a node isn't, it won't run in Quark at least, like a Pixie, but Quark itself is it's just a memory representation of a node. It's not an actual node.
Right, so like I wouldn't expect like to simulate Kong on a Quark node, quote unquote, right?
Yeah, maybe come up and chat a little bit later if that's okay, because I think I'm about to get kicked off the stage.
Can you SSH into a node and just start Pixie?
In Quark? No. Oh, just in general? No, not really. What you can do is you can put eBPF breakpoints in, and you can do that yourself just by SSHing into a node. Pixie itself is kind of like a suite of software that kind of needs to be installed But the kind of stuff that it's built upon, there's a whole bunch of like BPF scripts that you can go and install, but a lot of them are quite difficult to deal with because it's all written in like C, and it's very scary. But it's definitely possible, but not exactly recommended.
It's not easy to get past security.
Oh, yeah, no. It's never easy to get past security for clusters and eBPF, is it? Awesome. Well, thank you, everybody.